A DC motor looks like a small rotating cylinder with a few key parts that work together like a team. The armature is the rotating core. Think of it as a playground carousel that carries copper windings, loops of wire around its rim. When current flows through these windings, they become temporary magnets. The field winding, or permanent magnets in some motors, creates a steady magnetic field similar to the invisible force you feel when you bring a magnet near a metal nail. The commutator is a split metal ring attached to the armature shaft. It acts like a revolving electrical switch, constantly reversing the direction of current in the armature windings, so that the torque is always in the same direction. Finally, the brushes are small blocks of carbon that stay in contact with the commutator, much like a set of fingers, gently touching a rotating knob, delivering current from the stationary power source to the moving armature without getting tangled. Together, these parts convert electrical energy into mechanical rotation. The operating principle of a DC motor is based on Fleming's left-hand rule. A current-carrying conductor placed in a magnetic field experiences a force perpendicular to both the current direction and the magnetic field. In the motor, the armature windings carry current I sub E and sit inside the static magnetic field phi produced by the field winding. The force on each conductor creates a torque that makes the armature turn. As the armature spins, the commutator flips the current direction in each coil at just the right instant, keeping the torque pushing in the same rotational direction. Thus, electrical energy voltage times current is turned into mechanical energy torque times angular speed. This conversion is analogous to water flowing through a turbine. The water pressure voltage pushes the blade's armature windings and makes the turbine spin, delivering usable power. Torque in a DC motor is directly proportional to the armature current. The relationship is written as T equals K sub T times I sub E, where T is torque Newton meters, I sub E is the armature current amperes, and K sub T is the torque constant Newton meters per ampere. The constant K sub T depends on the motor's construction, the number of conductors, the magnetic flux phi, and the geometry of the armature. You can picture K sub T as a gear ratio that tells you how much turning force you get for each amp of current, just like a lever gives you more force when you push farther from the pivot. If you double the armature current, the torque doubles, assuming the magnetic field stays constant. When the armature rotates in the magnetic field, it cuts magnetic lines of force, and a voltage is induced in each winding. This is back EMF, EB. Using Faraday's law, the induced voltage per pole pair is proportional to the rate at which the conductor cuts flux. EB equals K sub E times phi times omega. Here K sub E is the back EMF constant, volts seconds per radian. Phi is the flux per pole, Weber, and omega is the angular speed, radians per second. Often K sub E equals K sub T, when SI units are used because both constants stem from the same geometry and magnetic field. The back EMF acts like a self-generated battery, opposing the applied voltage, similar to how a car's engine produces resistance when you try to accelerate faster. As speed increases, EB rises, reducing the net voltage across the armature resistance and limiting the current. The speed-torque characteristic of a DC motor is a straight line when plotted on a graph of speed omega versus torque T. The line intercepts the speed axis at no load speed omega naught, the speed when the motor runs without any external torque, so the only current is that needed to overcome internal losses. At the other extreme, full load speed omega F occurs when the motor delivers its rated torque. The current is higher, the net voltage across the armature falls, and the speed drops. Omega equals open parenthesis V minus I times R a close parenthesis divided by K E times phi. T equals K T times IA. Eliminating IA gives the linear relation omega equals omega naught minus open parenthesis K E times KT divided by R a close parenthesis times T. Thus, knowing the supply voltage V, armature resistance RA, and constants KE equals KT, you can compute omega naught when T equals 0 and omega F when T equals rated torque. This explains why a motor slows down as it lifts a heavier load. The extra torque draws more current, which reduces the effective voltage for speed. As the armature current produces its own magnetic field, it interacts with the main field. This is called armature reaction. The reaction tends to distort and weaken the main flux, shifting the neutral plane, the position where the induced voltage is zero, and causing a drop in generated torque. Imagine trying to walk straight in a crowd that pushes you sideways. You end up veering off course. To counteract this, designers use compensating windings, extra coils embedded in the pole faces that generate a field opposite to the armature's field, or interpoles, small auxiliary poles mounted on the rotor that create a corrective flux exactly where commutation occurs. Both techniques keep the neutral plane stable and reduce sparking during commutation. Commutation is the process of reversing the direction of current in the armature windings as they pass under the magnetic poles. The commutator, a segmented cylinder, connects each coil to the external circuit through the brushes. When a coil moves from the north to south side of the field, the commutator segment linked to that coil swaps contacts with the brush, reversing the current direction at the precise instant the coil would otherwise experience a braking torque. Proper timing prevents the coil from being momentarily forced opposite to the rotation, which would cause a large opposing voltage and result in sparking. The brushes, made of soft carbon, maintain a low-resistance sliding contact, absorbing the switching transients and keeping the electrical noise low. Think of the commutator brush pair as a revolving door that lets people, current, enter and exit a moving hallway armature without bumping into each other. Suppose a 240-volt DC motor has an armature resistance R sub A equals 0.5 ohms, torque constant K sub T equals 0.1 Newton meter per ampere, and flux phi equals 0.02 Webers, so Ke equals Kt equals 0.1 volt-second per radian. The motor drives a load requiring torque T equals 5 Newton meters. First, find the armature current. I sub A equals T divided by K sub T equals 5 divided by 0.1 equals 50 amperes. The voltage drop across the armature resistance is I sub A times R sub A equals 50 times 0.5 equals 25 volts. The net voltage that appears as back EMF is V minus I sub A times R sub A equals 240 minus 25 equals 215 volts. Back EMF is also E sub B equals Ke times phi times omega equals 0.1 times 0.02 times omega equals 0.002 omega. So omega equals E sub B divided by 0.002 equals 215 divided by 0.002 equals 107,500 radians per second. Converting to RPM, N equals omega times 60 divided by 2 pi approximately equals 107,500 times 60 divided by 6.283 approximately equals 1,028,000 RPM. A very high-speed motor, numbers chosen for illustration. This example shows how to calculate speed and back EMF from known voltage, resistance, and load torque using the fundamental equations. Typical exam questions. 1. Explain the construction of a DC motor. Answer should list the armature, field winding or permanent magnets, commutator, and brushes. Describe their functions and give a simple diagram analogy. 2. Derive the expression for back EMF. Start with Faraday's law E equals negative d phi by dt. Consider a conductor cutting flux phi at angular speed omega. Introduce K sub E and show E sub B equals K sub E phi omega. 3. Plot the speed torque characteristic for a given motor. Use omega equals V minus I sub A R sub A over K sub E phi and T equals K sub T I sub A. Eliminate I sub A to get a straight line equation. Omega equals omega naught minus K sub E K sub T over R sub A times T. Then mark no load speed T equals 0 and full load speed T equals rated. 4. Discuss armature reaction and how interpoles compensate it. Define armature reaction. Describe its effect on flux distribution and explain the role of interpoles or compensating windings. For each answer, begin with a plain English description, follow with relevant formulas, and finish with a short real-world analogy to demonstrate understanding.